Hello and welcome to this video on probability. I'm going to focus this particular one on independent events, and we're going to begin by talking about events being independent as they're occurring, not affecting the occurrence of the other. For example, if I'm rolling a die, the me obtaining a 5 when I roll a die is not depending on whether it's raining outside or not. These are independent events. So, how can you understand independent events? Well, independent events are said to be placed in a two-way street, let's say. You can say that events are independent because common sense dictates that they're independent events. For example, as I said here, the roll of the die and raining outside is like there's nothing that can relate one thing to another. So from there, we have that you know that they are independent. So as you know that they are independent, we can use the multiplication law. That is that the product of the intersection is the product of their independent probabilities. Or you can work the other way around. You can be asked, and this is a very typical question, you can be asked if two events are independent, and in that case, you need to see if they verify the multiplication law. And once you study this and this, and you can show that these are equal, then we can talk about them being independent. So this is like the way that we're going to be going over this. I'm going to be doing an exercise now where I'm going to be talking about how we can use this, but there's a very interesting variety in exercise that I recommend that you go and look for. And in particular, this that I had mentioned on how this question on how we can find if two events are independent by studying their probability. In this case, I'm presenting to you this exercise that talks about passing through three independent set of traffic lights. In this case, we are told that they are independent, hence we know that we can use the law. Remember that the law of the independent is the following, is that we have the probability of an intersection. In this case, let's call it A and B. This is the product of the probability of A times the probability of B. So this is what it means. And then we have to see, well, all of my possible outcomes, how is it that we can study them? So let's see. Let's start by the beginning. We are told that the probability that she has to stop at any particular set of lights is 0.2. I'm going to write that down as probability of stopping is 0.2. So let's see that what is the probability that she first has to stop at the second set of lights. What does that mean? It means that for the first set of lights, she didn't stop. So again, if the probability of stopping is 0.2, the probability of non-stopping, this has to do with the exhaustive events that we talked about in the first video on probability. This, I'm going to write it as S complement like this. This means that her non-stopping is 0.8 because they need to add up to 1. This means she either has to stop or not stop, and there's no, and she cannot stop and non-stop at the same time. It's either one or the other, and it has to be one or the other. So they must add up to 1, and hence these are the probabilities that are going to be used. So if she has to stop at the second set of light first, that means that for the first set of lights, she didn't stop. So it's going to be 0.8. And then for the second set of light, and this is independent, we can just multiply. We multiply because they're independent, and now she has to stop. So this is not stopping times stopping. So that is the probability of 0.16. That is the probability that she has to stop first at the second set of lights. What happens here? We're not using the third set of lights because we don't care about the outcome for that one. It's just first and second. For the third one, it will be either stopping or not stopping. It's not going to affect the probability we're looking for. What happens with number two? With number two, we have to consider that she has to stop at exactly one set of lights. That means that this could be expressed as stopping and then non-stopping, non-stopping. It could be non-stopping, stopping, and non-stopping, or it could be non-stopping, non-stopping, stopping. So essentially, the operation that we're going to be doing is the 0.2 for stopping, and then twice 0.8 of non-stopping. And this is going to be presented 3 times. So we multiply this times 3 because it's here, here, or here. Note that the order doesn't matter. If we multiply 0.2 times 0.8 or we do 0.8 times 0.2, it's the same thing. So essentially what we're doing here is, okay, yeah, we have 0.2 times 0.8 times 0.8 3 times. We do this and we get a probability of 0.384. Essentially a 38.4% of her having to stop at exactly one set of lights. Now to the interesting part, that is, has to stop at any set of lights. And here the trick is to think of it as in complements, because yeah, you can go and say, yeah, okay, so if she has to stop, it could be that she stopped and then she didn't stop and then she didn't stop, or that she stopped and then she didn't stop and then she stopped, or that she stopped and then she stopped and then she stopped, or that she didn't stop and then she stopped. And you can be like going on forever doing that, but there's a very simpler way to go around this, because if you think about it, stopping at any set of lights is mutually exclusive to non-stopping at all. It's like she either stops eventually in some set of lights, or she doesn't stop at all. So what you can think is, well, so the chances of her non-stopping at all, that will be this, non-stopping, 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 this would be 0.2 times 0.2 times 0.2, essentially 0.2 cubed. This is the only outcome that we don't want. We want every outcome except for this one, because this is the only outcome where she doesn't stop, and we don't want this. We're looking for has to stop eventually. At any set of lights, she has to stop. So what is the probability here? Well, the probability is going to be 1 minus 0.2 cubed. We are essentially subtracting all of the possible outcomes from this one. And then this gives us a 0.488. So there's a 48.8% of chances that she has to stop at any set of lights. I believe that I mentioned this in a previous video, that thinking of an exercise in terms of complements is very useful. Essentially, when you find something like this, that if you were to think of it in terms of the favorable outcomes, there were a lot, because it was stopping, stopping, non stopping, 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 non stopping. It was crazy. So if you take like 10 seconds and think of it, you can usually find a way that's going to make it very easier for you to get to the solution. So, as usual, you can find more exercises in the link to my webpage. Please feel free to go over that and write back to me if you have any comments or suggestions. Thank you for watching, and we'll see you in the next video.